Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Loren Matilsky with us today. Hey, Loren.
Hi, how's it going?
I am doing awesome on this Tuesday, December 13th, as we record this. And I'm in Phoenix, and we are definitely in our winter weather, such as we get here in Phoenix. So it's all good. And Loren, where are you located at right now?
I am at my parents' house in New Jersey. So
Cool.
also a little wintry here, but more rainy and gray.
No snow yet, huh?
No snow. And I just got back from England actually
Huh?
for an international conference, and it was even grayer and rainier there. So I'm used to it at this point.
I've been to the UK once or twice. Yes, it's a little on the grayer side. Yes.
Yeah.
Very cool. And what is your position? Where are you at institution wise?
Right now, I'm an NSF astronomy and astrophysics postdoc
Cool.
at University of California, Santa Cruz.
Very cool. Congratulations.
Yeah. So
Very
I just
cool.
started that. I'll be there for about 3 years.
Okay. Ooh,
Yeah.
Santa Cruz. Oh, that's to the scene of the crime for me. So that's where I did my graduate work, was at Santa Cruz.
Oh, nice.
So,
Go banana slugs.
go banana slugs, go redwoods. Yes.
Yeah.
Very cool. Very cool. And Loren, what do you like to do for research?
So I study the magnetic fields of stellar interiors.
Cool.
So basically, the sun has solar flares, coronal mass ejections, things that we care about on Earth. And then as we discover exoplanets, it turns out other stars have the same types of things, but even more sort of violent than the sun. And so I've been studying how those magnetic fields are produced in like a general stellar context.
Very cool. Very cool. Yeah. And that is going to bring us to this very awesome APJ letter. It's open access, people. You can go get a copy for free. Go grab one. Confinement of the solar Tachocline by Dynamo action in a radiative interior. And Loren, take us away.
All right. Yes. So this is the culmination of the final chapter of my PhD. I just finished my PhD in Boulder, Colorado, with Yuri Tomre and Brad Hyman. They were my primary thesis advisors. And I'll give a shout out to all my co-authors. So this paper actually had quite a few. There was Brad and Yuri, who have kind of been with me the whole time I was in Boulder.
Cool.
Yuri Tomre in particular is kind of a veteran of what's called helioseismology, and I'll actually talk a little bit about that for the introduction. But really was instrumental to the field, and one of the things they discovered was this Tachocline, which I'll also find. So Yuri has been very interested in the Tachocline for 20 to 30 years, and as a grad student, I didn't know what a Tachocline was at all, and so probably the avenue of research was very much influenced by Yuri Tomre. So sure, I owe him a debt of gratitude for that.
There you go, Yuri. There's a shout out.
And then Nick Featherstone is also was very instrumental to this work, basically figuring out, first how Nick wrote the code that we use it's now open source.
Yay.
He knows it back to front, and I was doing some things wrong, and he fixed those things and also helped out quite a bit with the dynamical interpretation at the end.
Nice.
And then Catherine Bloom is a new grad student, and she just passed her master's thesis, so not so new at this point, but she's a grad student in Boulder as well. And she was extremely helpful toward the end in making that final figure. Actually, we'll come to that at the very end.
All right.
And that kind of bleeds into her research. Anyway, great team of collaborators. Was happy to work with them.
Cool.
Okay, so for this paper, there's a few things we sort of have to define. Most of them are in the abstract. The first, is the solar Tachocline. So what is a Tachocline? Tachocline is sort of analogous to what's called the Thermocline in the ocean. So in the ocean, as you go down at a certain point, everything sort of goes toward the same temperature. So it's called a thermo temperature cline, all the same. And in the sun, tach is speed, and what the Tachocline is, as you go down in the sun, eventually everything rotates at the same speed.
solid body. Yep.
Yeah. And so helioseismology basically directly measured that. What helioseismology does is it looks at the seismic oscillations on the solar surface, and then you can figure out things about the interior. And what was discovered around 1990 is that the surface layers rotate differentially. So the equator goes around about 30% faster than the poles. And then at the base of the convection zone, which is the region that occupies the outer 30% of the sun, everything just transitions to like a solid ball. So from all outward appearances, it would seem like the inner 70% of the sun just rotates like a solid ball, which was not, suspected that would be true. So it was a surprise for that reason, but also dynamically, it's a major mystery why there can be a boundary layer that thin, because basically something has to force the interior to rotate like a solid ball. If it were just left to its own devices, then diffusion would spread the differential rotation from the convection zone into the interior.
Yes.
And so about the Tachocline was discovered, this seminal article, it was probably somewhere with Spiegel and Zahn, 1992. I forget exactly where it appears.
Spiegel and Zahn.
That should be right up front. They realized that this was actually dynamically an issue, and that there had to be something confining the Tachocline. And what that something is still very much a subject of debate in the community. There were two, it's not like there's been no work done on this. A lot of work has been done. There were two main explanations for what could confine the Tachocline. So the first was actually given in Spiegel and Zahn, 1992, and this was basically shear instabilities. If you shear a fluid, it can become unstable and turbulent, and that kind of can mix things like the angular velocity, and that could make the thing rotate like a solid ball. Spiegel and Zahn argued.
I'm with you.
The next seminal paper, which is, I forget where it appears, Goff and McIntyre.
Okay.
Yeah, they're 1998. Actually argues that shouldn't work, because those same instabilities in the Earth's atmosphere, for example, would drive things away from solid body rotation. So they said that mechanism that Spiegel and Zahn proposed really couldn't be accurate. And instead, there had to be a magnetic field. So this is I believe, a Nature paper from 1998, which is the inevitability of a primordial magnetic field of a magnetic field in the sun's interior, or something like that. So they were like, there has to be a magnetic field.
Okay.
And basically the research over the next few decades is more or less aligning with Spiegel and Zahn. So not a magnetic field, or there is a magnetic field.
Okay. Right.
And so that's kind of the setup for what this paper was aiming to address. So basically, we ran a global simulation where it seems like the magnetic field that gets produced self-consistently by a dynamo can actually confine a Tachocline. So I think this is some major progress.
Cool.
By no means is the Tachocline problem like completely solved, but I think we are one step closer to understanding what's going on.
Progress of science, yes.
Yeah. So, and then right before I get into the main results, I should mention that with the Goff and McIntyre model, they were thinking of like a primordial, weak magnetic field from the sun's birth.
Okay.
And there's another, it's a similar model, except in that case, the magnetic field comes from the solar dynamo. So the sun goes through a 22-year cycle where the magnetic field gets stronger every 11 years. It reverses, making a 22-year cycle overall.
Right.
And the idea was that field could kind of penetrate down into the Tachocline region and confine the Tachocline that way. And this paper is more in line with that kind of second cyclic magnetic field scenario.
Okay.
Yeah. So yeah, we can, I guess, dive into the main results. So what we did is we ran a global simulation with the Rayleigh code. So the Rayleigh code is, again, was originally developed by Nick Featherstone. It's now open source. So actually you can go download it on GitHub. And if you have access to a few thousand cores on a supercomputer, then you can run these models.
Yes.
And it should be entirely reproducible, which is
Very good.
a good thing.
Yes.
This code has a long history. So it was originally developed by at Los Alamos by Gary Glatzmaier, Peter Gilman. So they laid out the groundwork, really, I think Gary Glatzmaier, of basically decomposing variables in a theme appropriate for a sphere, which means spherical harmonics. So things are decomposed on spherical harmonics, and then you can do different things, but usually Chebyshev polynomials in radius. And so you expand all these fluid variables, and then you can compute things like derivatives very simply and accurately using the properties of spherical harmonics.
Yes. Very cool.
The code is nonlinear, so the main feature of the fluid equations is they are nonlinear, and so you can't do everything with the spherical harmonics. And actually, most of the time spent by the code is in physical space, where we just kind of transform back into like functions on a grid, and then multiply things together and compute nonlinear terms.
Got it. Got it.
And that's really the essence of these chaotic Dynamo simulations. So what we did here, I should also mention the code is highly parallelized, which is so that allows us to do larger problems. I think it's the biggest test has been something like 100,000 cores. Cool. So you can really scale things very well to like large problem sizes. I only used, I don't know, 4,000 to 8,000 cores for this, so not the full. But it's still a great tool for doing. If you want to simulate spheres, which I do all the time.
And I think Gary is at he's at Santa Cruz, yeah, or he was at one point.
Yeah, I'm not sure if he's still there. He was, yeah, because he was a variety of places. I think he was at High Altitude Observatory in Boulder for a while. He might be. Yeah, it's funny. I just moved to Santa Cruz, so I'm actually not sure of all the people here. Yeah.
Okay. Very cool. All good.
So, so what we did for this experiment is we simulated a convection zone. So this would be basically an unstable layer to convection. So there's hot fluid down below that overturns, cold fluid falls. It's not the full solar convection zone, but it's like the bottom, most of it by radius, but we ignore the outer surface layers of the sun is the main thing. So the outer surface layers are where everything's like radiating. You get magnetic reconnection, you get solar flares, you get horrible things, ionization. I think you even get like molecular dissociation. Yes. Yeah, and so we don't want to deal with any of that. We want an ideal gas, so we kind of shave off those outer layers. And then underneath that convection zone is a stably stratified region. So what happens is the convective downflows penetrate into the stable region. And there they can excite other things like stable stratified waves. And we looked at two of these simulations. So they're identical, except one case has a magnetic field and one does not. Okay. So what we do is in the case with no magnetic field, we just solve the non-magnetized, or Rayleigh solves the non-magnetized fluid equations. And the only difference for the MH, so we call this the HD case, and then for the MHD magnetohydrodynamic case, we start things off with a small seed field of of about 1 Gauss. So we run things dimensionally, and then the MHD case develops a dynamo, which means that it's kind of self-excited conversion of kinetic energy into magnetic energy, and then that initial field grows by about a factor of 1 to 10,000. So ultimately, the MHD case has a pretty big magnetic field of about 1,000 to 10,000 Gauss.
Okay.
And so those are the only differences, but then the MHD case really ends up being quite a bit different. So that I guess we can probably go to the first figure.
Okay. Good. Let's take a look at this.
So this is the main result. As the upper left, so panel A, on the left-hand side, we have the differential rotation in the HD case. And so in figures like this, what we're doing is we average the rotation rate. So kind of the how many times it goes around per day or whatever. And then we're looking at a meridional cut. So we're kind of slicing the sun like an orange. That y-axis is along the rotation axis.
Yes.
The middle, where the x-axis would be, is along the equator. And then the origin would be the center of the shell. And then as you go outward, you get to the near surface layers of the shell. And that dashed black line is the boundary between the convective layer and the stable layer.
This round one. Okay, got it.
Yeah. And then the dotted green line is where those plumes, so the plumes overshoot into the stable layer, and kind of where they stop is where that green line is. So the green line is like the depth of the overshoot layer. It's quite thin, as you can see, so the plumes don't get very far, but they get, a little bit past that transition. So what you can see from the left-hand side is that we plot the rotation rate. So fast rotation is red, slow is blue.
Okay. Yes.
And I guess we didn't see, if you look at the sun, basically the convection zone of the sun looks a lot like the figure on the left. So the equator goes around fast, the poles go around slow.
Right.
And there's strong differential rotation in between. And that differential rotation goes all the way into all the way through the convection zone. The difference here is that on the HD case on the left, the rotation has diffused all the way into the radiative interior. So what that means is that the radiative interior is rotating differentially as well.
Okay.
So that's different than the sun because there's no tachocline. Everything is just rotating differentially.
Okay.
And if we move to the right, that's the MHD case. You can see it looks quite a bit different.
Yeah.
First, the differential rotation in the convection zone's a bit complicated. It's not fully solar-like. But the really interesting thing is that there seems to be some sort of tachocline. So in the radiative interior, everything converges to basically the same rotation rate.
Yes.
And there's so that's different. And we know that it has to be magnetically caused because one case had a magnetic field and the other one didn't. Naively. And then we'll get into what is actually happening in a bit. If you go to
hold on, the magenta circle.
So the magenta. So if you go to the figure on now panel C, magenta was just chosen by me sort of where that solid body rotation is really achieved, and it's pretty much arbitrary. It corresponds to I think I ended up choosing where does the rotation contrast fall by a factor of 20. But really by eye, you can see that below the magenta line, things rotate like a solid body.
Yes, exactly.
You can see that this looks actually quite a bit different than the solar tachocline. So, and this is one of the reasons why we really haven't solved the problem yet, because the differential rotation in the convection zone is not exactly solar-like. So it gets decreased compared to the solar case as well. So the magnetic field is trying to eliminate differential rotation everywhere. It just does so much more efficiently in the radiative interior. And that's why it yields this tachocline-like layer. And then the other thing is that in the sun, there's the tachocline is thin, so that in the sun, that blue line would sort of be flat in the convection zone, and instead it's kind of very much sloped in the convection zone.
Right.
So anyway, there's definitely some differences, and I think the main question going forward will be, how do we get this mechanism to work while also retaining
all the desirable properties? Yeah,
exactly.
Right.
And then the next two figures are just the amplitudes of the velocities. So, and the only thing that's important here is that so I plotted V theta and V phi. These are the horizontal velocities,
right?
And then VR separately. And so in the overshoot layer, you can see that VR just falls by a lot. Like 1,000 in the overshoot layer, and then down below, I think it's a factor of 10 to the 6th. So VR just plummets, and you'd expect this because in stable stratification, things can't move vertically. The horizontal velocities sort of plummet as well, but definitely not as much. And the punchline I think I'll throw out is these strong horizontal velocities are seen in honestly all global simulations I'm aware of. I shouldn't say, you should never say all, because
right.
But
most of the ones I really know
tend to show up, and I think they're actually causing dynamical effects. And so I think for us modelers, it would be, that's my plug, is we should really figure out where these horizontal motions coming from, because ordinarily we regard the stable interior as very like quiescent. I mean, there's no convection,
right?
So there's not a lot of
fluid motion.
But then there are these horizontal velocities. Anyway, that's the main point of this figure, and we'll talk more about that at the end. The next one is the same thing for the magnetic field. And the main thing to say here is that the fields are strongest in the overshoot layer. So they kind of spike in the overshoot layer. You might expect, because there's like a tachocline there, and the tachocline, I forgot to mention, is a key player in the solar dynamo, we think, because the tachocline has a lot of shear. And so to create the magnetic field associated with the dynamo, we need a lot of shear somewhere. And so when the tachocline was discovered, it was given kind of a lot of importance in a lot of theories about the dynamo. So that's actually, I should have mentioned that before, because that's one of the main reasons we have to figure out why there is a tachocline in the first place. But yeah, so the main thing about that figure is that there's magnetic field everywhere. So it spikes in the overshoot layer, and then it's also present in the radiative interior. And I think that's also a key thing. So it definitely falls off, but there's sizable magnetic field down there. Only falls off by a factor of 10 or so. And that's the other indication that this confinement is happening magnetically. Cool. Very cool. Okay, let's see, where are we here in the paper? The next figure, maybe the next figure is, so this is what the magnetic field actually looks like. These are Mulwady projections. So you take the full sphere, project it onto a plane. And I've chosen 2 levels. So the top row is base of the convection zone. Bottom row is in the middle of the stable layer, so below all the overshoot. And what I'm showing is the B phi and B theta. These are the 2 horizontal fields. They're plotted in color. So positive red, negative blue, and then their product on the right. And so the first thing to notice is that these fields are non-axisymmetric. So
Fair enough. Yes.
a lot of the time, like with the Earth's magnetic field, it's kind of the strongest component is the dipole, which is the same at all longitudes on the Earth.
Yes.
This is definitely a lot different. This is more, well, we call it M equals 1 because
Yes.
dipole is M equals 0, or axisymmetric is M equals 0. This seems to be more M equals 1, which means that there's one node in longitude, or M equals 2, which means there are 2 nodes in longitude.
Yes.
That's a little bit different than a lot of dynamo simulations. It's definitely different than what people are thinking usually when we think about these magnetic confinement scenarios. And I think this is actually a boon to us. And it's one of the reasons that this works so well to confine the tachocline. But the other thing that I should mention is that, first of all, the fields are connected. So clearly, the radiative interior knows about what the convection zone is doing, or vice versa. The fields are a lot smoother in the in the stable layer, which you might expect because there's less kind of pummeling of these plumes. And then the final thing is that if you take those fields and multiply them, there's a very noticeable correlation. So the product is positive in the northern hemisphere and negative in the southern hemisphere. And you can look at the equation for magnetic torque, and it turns out that this correlation means that they're sending angular momentum poleward. And so what that means is that as the differential rotation tries to imprint and speed up the equator, the magnetic field is sending that angular momentum away from the equator toward the poles, and that's maintaining solid body rotation. So this is kind of the first real indication that, yes, it's the magnetic field maintaining solid body rotation. And then explicitly we show that in the next few figures. And then the bottom it's a little bit weird. So normally we think of butterfly diagram. So in the sun, you can plot like where sunspots emerge as a function of time, and you get these beautiful like butterfly wings. So they first appear at mid-latitudes, then closer to the equator. That traces out a butterfly wing. The butterfly wing color reverses every 11 years, because if you think about like the average field, the polarity reversals reverses because of Hale's law. So that's normally how we plot these things. This situation is a bit different because, well, M equals 0. So normally you plot the longitudinally average component, but our average is nearly 0. So instead, what I've done is plotted the M equals 1 part. And the way that works mathematically is you like you do a Fourier transform to M space, and then it's a complex number, and so you don't want to show just the full part. And so I've shown the real part of the M equals 1 component of B theta. And the other addition is that this is time radius. So instead of looking at like a butterfly diagram with time and latitude, we're looking at time and depth. So so the overshoot layer again is near the middle. And so, yeah, you can see that the field sort of first is strongest in the overshoot layer and then slowly makes its way into the radiative interior. Or you could also maybe convince yourself that the field appears in the convection zone, then goes down, gets amplified in the overshoot layer, and then goes down. I'm actually not sure. I look at this plot on different days and feel differently about it. So I think things are kind of happening in the overshoot layer first, but anyway, it's a little bit unclear actually. So, but it does seem like the radiative interior at least responds later. So things are happening in the convection zone or overshoot layer, and then later things respond in the radiative interior. And then these slanted lines are effectively diffusion. So this is where in the first part, when we talked about confinement, there's the primordial field, and then there's also a cyclic magnetic field.
Okay.
So if you have a cyclic magnetic field, then it can penetrate up to a skin depth. So it's the same thing if you shine light on a conductor, for example.
Right. Yes.
Light will penetrate to a skin depth. My skin depth is big because my magnetic diffusion is very big.
Yeah.
And those slanted lines are basically the rate at which the field would diffuse inward
on its own.
Yeah, from this skin effect.
Correct.
Because the cycle is you can, it's like every 500 rotations. Anyway, so that's where those slanted lines are coming from. And you can see that they sort of match the rate at which the field diffuses. So I think a primary effect here is the diffusion. So there's this skin effect kind of pumping field downward. I should, well, there's a background here that maybe is, I don't know how deep I should get it. Most people, usually when you run a global simulation and you want there to be a tachocline, the way you do it is you lower the diffusions fairly drastically in the radiative interior. And that basically stops the field from diffusing down temporarily. Right. So as long as you can lower them enough and you don't want to simulate for a very long time, then you can effectively have a tachocline because the diffusions are so low.
By design.
And so that's historically what's been done. Of course, if you do that, then you really can't study tachocline confinement because
you're putting it in. You're putting it in.
There's nothing to confine. Anyway, so that's one difference. If you're watching this and you know a lot about these global simulations, these diffusions are actually quite high in my case. So I did not plunge them. Anyway, nice. So that's why you can get this skin effect type thing.
Okay, good.
Yeah.
Thank you.
Yeah. Okay. Then let's see what we should
and we've got some ugly equations on the magnitudes of the torque. I'll cover torque.
So you can look at the actual torque and how much, this gets a little complicated. So the equation 1 is the primary equation. So that's the torque equation. The first term is basically viscous diffusion. So that just sends whatever's in the convection zone down below. You can work this out. There's signs of theta and stuff, but mostly it's just a diffusion term. So if there's a gradient in rotation rate, this term will try to smooth that out. The other term and the other term, which is the first two are the only really important ones. That one is the magnetic torque term. And there, if you work out the math, you can actually see how the product of B theta and B phi we showed before actually sends momentum poleward. And effectively what this is doing is it's balancing the viscous term. And that correlation between the colloidal field B theta and B phi is what is causing that torque. And then the final one is one that we actually don't care about, but we should plot it for completeness. It ends up being negligible in tachocline. You can also get velocity correlations and circulations that can transport angular momentum. It turns out in this case, they're not relevant, but they can be relevant. So in the convection zone, they're probably important.
Larger for sure. Okay.
I think I will skip the next few equations and also, first, let's look at figure 3A. Let's ignore figure 3B and C. It's a little bit technical and not, I think, as important as So figure 3A is just showing that the viscous torque is doing what we'd expect. So there's differential rotation near the equator, and so it's trying to send that equatorial jet into the tachocline. So this is torque averaged over the tachocline.
Yeah, okay.
And so the viscous torque is positive near the equator, so that's trying to speed things up, negative near the poles, trying to slow things down. Viscous torque wants to put differential rotation in, and then you can see that the magnetic torque just basically opposes that.
Correct. Right.
So this balance really, so it really is the magnetic field that is
driving,
confining the tachocline, and so that's the math proving it.
Cool.
And then, okay, so that's the main result of this paper, is that we have solid body rotation in a magnetized case, and it is the magnetic field that's forcing the solid body rotation.
Nice.
So this is, I think, on its own a major step forward, because this is 3D, it's nonlinear.
Yep.
Essentially a more complicated version of this scenario where the magnetic field is being caused by the solar cycle. So the cyclic magnetic field diffuses into the interior and confines the tachocline.
Okay.
The other thing, though, that's important here is that it seems like diffusion is not the only thing that's going on. So the question, I mean, in this model is, where is the magnetic field actually coming from?
Yes. Okay.
So we have a dynamo in the convection zone, but deep down, I mean, there's field everywhere, as we saw from the first figure. And so, and it turns out it's not just the diffusion. So it's a bit complicated because there is diffusion. And so there might be a magnetic field even if the dynamo didn't extend deeper down, but it actually seems like the dynamo is extending deeper down.
Yeah.
So the way we saw that is the next equation. So this equation 4 is the induction equation.
Royal of the MHT. Yep. Okay.
Yeah. So basically, you have this is the normal MHD induction equation. The magnetic field can change in two ways. It can change by inductive motion. So this is like convective stirring, or those horizontal velocities that we talked about. Basically, inducting, changing little circuits across magnetic field lines that creates an inductive effect via Faraday's law. And then the other thing that can happen is it can diffuse. And so the diffusion is what we kind of expected to see, because it looked like things were sort of diffusing to a skin depth. You can work out what are the two relative contributions to the magnetic field. So we did this separately for phi. And I think you can also break up the induction into its various components, like shear, compression, and advection.
Yep.
Maybe we won't discuss that and just focus on the top part, which is induction and diffusion.
Okay.
Because essentially you have a dynamic way you can get field, which is by stirring, and then you could have diffusion from above.
Okay.
And you can look at this for both phi and theta. And then in the next figure, that's what we see. So what I've done here is you take the induction equation, make it into an energy equation. So you multiply it by B phi. So this is the evolution of B phi squared. So the magnetic energy,
right,
as a function of, so you can average over time. So the time derivative goes away. You get a balance between inductive production of energy and diffusive production of energy. And what we sort of expected to see, well, for phi, we got what we expected. So there's induction is positive. It's creating phi magnetic energy.
Yes.
And diffusion is destroying it. And also you can work out that it's mostly shear. So in general, with these dynamos, this is what happens. There's a little bit of shear. Even in our solid body rotating case, there's still a little bit of shear. And so it takes colloidal field and smooths it out into toroidal field. So this makes sense. And the surprise here is that then if you go to the right and you look at the production of the colloidal field,
Okay.
really in any of these confinement scenarios, it's the source of the colloidal field that's really important. So for Goff and McIntyre, it was a primordial field that was just kind of sitting there. For the other cases, for the cyclic magnetic field, it was a cycling colloidal field that diffuses to a skin depth. And then for us, we thought it was the same thing of just colloidal field diffusing downward. But on long time averages, it actually seems to not be that. It actually seems to be inductive. And so this is a surprise, and it's an open question how this is happening. So basically, we have that on long time scales, the maintenance of the field is actually inductive and not diffusive. So this is an open question. So this is kind of the next kind of speculative, because we didn't solve this. We don't exactly know what's happening. We know it's the horizontal velocities, so you can work out where that induction is coming from. And it kind of has to be the horizontal velocities because the vertical velocity is so small. And I just want to throw it out there for the other researchers is we see strong horizontal velocities. I would say in most of all of the simulations I've run across, maybe not all of them have it, but it seems to be very common to have strong horizontal velocities. Okay. The other thing that seems to be common is there to be strong magnetic field when we simulate things and have a stable layer. And I would say that is not adequately explained because a lot of these other simulations actually do have a tachocline via this drop diffusion. And if that were true, it is true, they have the low diffusion, they have a tachocline. They also have magnetic field. The magnetic field maybe is not getting there by diffusion. That's my sort of speculative hypothesis. And the fact that we're seeing in all these models strong velocities and strong magnetic fields suggests that maybe there is a dynamic mechanism going on. And this would mean that the dynamo effectively isn't confined only, when you say dynamo, you have to be careful. So I guess dynamic amplification of field, inductive effects, is not confined to the convection zone. Okay. And if that were true, then this would be basically a whole other mechanism for the creation of magnetic field and stable layers, which I think we don't know. I think a lot more work needs to be done. But if you could get dynamic amplification of field and stellar interiors, I think that would be a major change in how we view, because normally we view the stellar interiors as these nice quiescent inactive reservoirs that sort of accept whatever the convection dumps in from above and just sit there. And if instead they're dynamically active, then I think that's a game changer.
Yeah, absolutely.
So that's nearly it. And this is where we're now in speculation. So first, we're speculating that there's we know that there's dynamic amplification in this case. Yeah. We suspect maybe there's dynamic amplification in other cases as well. Okay. And the other thing is that we need to know the source of the horizontal velocities.
Yes.
So the other thing that speculation actually leads into Catherine's research. And so I'll end on that. That's the final figure. So Catherine Bloom made this figure. She knows a lot more about this stuff than I do. It turns out that because my case was rotating like a solid body in the interior, you can get Rossby, like really nice Rossby waves.
Yes.
which is interesting. So Rossby waves appear everywhere. Again, Catherine's more of an expert on this. But from what I understand, they appear in the Earth's atmosphere. You have jet streams, you have the Gulf Stream, you have anytime you have something kind of moving on a flat surface, so in 2 dimensions, and there's a strong influence of rotation, you get these Rossby waves. They come in different flavors, and one particularly simple flavor is when the system is just rotating like a ball. These are also called planetary waves. And so essentially, because the radiative interior was rotating like a solid ball, in my case, you get really nice Rossby waves. So what Catherine did here is she plotted a power spectrum of the radial vorticity.
Okay.
So this is radial vorticity is essentially the horizontal motion. And so you can decompose things as a function of m, the azimuthal order, and a function of frequency. And then you can, and so you see that these ridges of power appear. And the black dots are where the power would appear if these were classical Rossby waves. And you can see that they align basically very well, especially below m. And so these are really Rossby waves.
Cool.
And this is down below. So on the left is deep in the radiative interior. There you can really see. I mean, it's Rossby waves. In nearer where the Tachocline is, it's a little bit less clear. And so there still are Rossby waves. The reason we're interested in this is we want to know where the horizontal motions are coming from. And so down below, I think it's Rossby waves. Unfortunately, where the induction is really happening in the Tachocline, it's Rossby waves and also other stuff. So there's this smooth stuff. We really don't know exactly what it is. It could be shear instabilities. There's magnetic shear instabilities. There's joint buoyancy and magneto shear instabilities. There's all kinds of stuff that could be happening.
Complicated region. But
it could be Rossby waves. And so, so the other speculation is, first speculation, these horizontal motions seem to be causing induction. The second speculation is that these maybe could be Rossby waves. And so this was sort of a proof of concept that this kind of scenario could work in a global 3D model. And I think the next steps are really, I think us global modelers really have to figure out where are these horizontal motions coming from, because they've been there for like a long time. I think they might be actually doing something relevant. And we don't really know where they are. I should mention that we do know that there are gravity waves in these models. Lucy Alvan, you can look at the citations of the here, but she and Sasha Brun, one of our collaborators in Paris, figured out that there are gravity waves in these models, but these don't seem to yield the horizontal motions. And so it could be Rossby waves, it could be other instabilities. I think we need to figure out what's going on. Cool. If my speculation is at all justified and dynamo amplification could happen in stable layers, I think that also is really an important thing to verify. And I think that's basically it. I mean, to summarize, we have a 3D nonlinear simulation that seems to run a magnetic confinement scenario. So that's good. That old magnetic confinement scenario. And I've been there's a citation. I unfortunately have a hard time pronouncing the names. I think but there's Goff and McIntyre. The other one is Forgot-Stachka. Anyway, so we show that Forgot-Stachka scenario maybe is relevant in a more complicated case.
See that immediately, but okay.
It's
fine.
Anyway, and then the other thing is that the radiative interior might be a lot more dynamically active than we think. And that's basically it.
Very cool.
Yeah.
And if people are interested, we got 2 appendices, one on the background thermal state and one on the non-dimensional used in the simulations, Rayleigh numbers, Ekman numbers, and so on. So very cool. Very nice.
And one other thing is that if you are a modeler and you want to like check out this, we've started putting our simulations online, so you can actually go to Zenodo and download not the full simulation.
I was going to say it must be
the checkpoint and some of the basic stuff.
Cool.
And so that you can actually, if you want to like tweak things and run the case, you can do that.
Yep, verification and then tweak some verification. Very good. Yeah. Very cool.
And then there's the citations that I've been. They're a Hungarian group, and I just don't. I'm not very good at pronouncing the names. It's down there. Forgats Jachka. There's
here we go.
2001.
That's how I would pronounce it, I guess.
Yeah.
Okay.
So yeah.
Very nice.
That's it.
Very nice. Loren, thank you so much for walking us through your very lovely article.
Thank you.
Really great. So you mentioned it a couple times. Sort of next steps on where these horizontal velocities have to come from. And so let me ask a little bit more, a little bit more detail on immediate next steps. So let me ask one question. Even though you're running these on, let's say 1,000, 4,000, 10,000 cores,
right.
How long does it take to go from when I start to when I get a finished simulation that I can do some analysis on?
Right.
1 week, 1 month, 6 months?
In real time. Like
wall clock
waiting, I would say a few weeks. So these need to run kind of cogitate for, I submit them maybe 4 times each at 5 days at a time. So like I would say 3 weeks of 2,000 hours. So you don't want to pay by the hour.
No. 4 hours. Absolutely. 4 hours. So more immediately, where do you over the next couple of years, is there anticipation of doing additional simulations to figure out where these horizontal velocities are coming from?
Yes. So actually the NSF proposal that is now funding me for 3 years has the Tachocline in it as a central theme.
Nice.
And so I think this work basically lays the groundwork for trying to figure out, among other things, how the Tachocline is confined in global models. So in the NSF, what I'll be doing is looking at a solar case, also fully convective M dwarfs, because the lower mass stars and dwarfs, we discover a lot of planets around them, and they seem to be highly magnetically active. And they also can't have a Tachocline because they're fully convective, or seems very unlikely that they'd have a Tachocline. There's no stable layer. And so, the influence of the Tachocline is once again, it's important to figure out. So the proposal is basically, if you have a Tachocline, how does the rotation rate affect the magnetic field if you don't have a Tachocline? So I'll be running a lot of these cases over the next.
Very cool. What are some of the main machines that you use? Are these NF?
I've been using Pleiades at NASA Ames. I'm also going to apply for NSF Exceed, I think.
Yes.
Actually, I need to do that.
That reminds me over Christmas, so you need to get your time proposal.
I don't exactly know what we've been using NASA time for like a really long time, and so I'm very familiar with those sort of application cycles. I'm less familiar with NSF. I just started NSF, so I need to get up to speed on that.
Very cool.
But yeah.
Awesome. Well, I really look forward to seeing your future simulations come forward and seeing this field move forward a little bit on Tachoclines and how and why they are made. So very cool.
Yeah.
All right. That'll do. Once again. Right. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
All right. Bye.